Now that we've talked about decay and what radiation is for an atom, we can talk about how fast that happens. And how fast that happens is the decay constant. This is the number of particles that decay in a given time is proportional to the total number of particles we have in a sample. That means that the more particles we have, the faster decay rate we're going to have. So lambda is called the decay constant and determines how fast we're going to decay. The decay rate or activity R of the sample is defined as the number of decays per second. So this is decays per second, and is equal to lambda times the number of atoms that we have. The decay curve is exponential. The more we have, the faster rate we have of decay. So the decay curve follows this equation where we have an exponential, which shouldn't be a surprise, and the negative means that we're going to slope down instead of sloping up, and that lambda is the same. And when we talked about kinetics before, we talked about one-time constants and such. We want to find a point on this graph that will tell us what the decay rate is. And the handy thing to use in radiation is called the half-life. How long does it take until you have half of your sample left? So basically take our initial number, divide that number in half, and we'll find the half-life. So this is our symbol for the half-life. Is equal to the natural log of 2, because we have an exponential curve there, divided by lambda, which is what we get if we basically substitute out n is equal to half and naught. And so this is just another form of it, which we can also write as n naught over 2 to the n, because 1 to the n is just 1. And the units of decay are most often we'll do the math in decays per second, but we'll find in books Curies or becquerels. And Curies is obviously named after Madame Curie, who was one of the first pioneers in radiation. She paid the ultimate price for this work because we didn't know that radiation was dangerous when she was first working on it, because she was one of the first discoverers of it. And so we later find out that it can be extremely hazardous to your health. So here we have the half-life of iodine-131 is 8.04 days. So that's that T1 half. We want to calculate the decay constant for this isotope. So that's going to be lambda. Find the number of nuclei necessary to produce a sample with a radioactivity. So here we're going to want to find R. Or we have R, we're going to want to find N. And then suppose we have an activity of a certain sample is this number. So we have R. We want to find out how many half-lives have passed. So we'll start out first with part A. So for part A, we have the half-life, and we want to find lambda. So I'm going to solve this equation for lambda. Lambda is equal to the natural log of 2 divided by our half-life, and that gives us the natural log of 2 divided by 8.04 days. And we want this in seconds, so I'm just going to divide by the number of seconds in a day. So seconds per day, 80,000 seconds, equals 9.97 times 10 to the negative 7th decays per second. Alright, so that was easy enough. We just used the formula we had. The next thing we want to do is we have R, we want to find N. So I'll take the equation that we had on that first equation slide and solve it for N. I'm not going to use the middle part because we just found lambda, so we take that lambda, put it there, and we're given an activity R in Curies. We can't use those same units, so on our way we're going to have to do the unit conversion. So this is going to equal the rate up here, because we just found lambda. So we have 0.5 times 10 to the negative 6 Curies, and we need to multiply that by 3.7 times 10 to the 10th decays per second per Curie, because that's just a unit conversion. And then 9.97 times 10 to the negative 2nd decays per second. So that all cancels, the Curies cancel. So I get my number of atoms is 1.9 times 10 to the 10th nucleotide. Okay, so that's how many we have. Now we can figure out how many half-lives have passed after 40.2 days. So the number of half-lives that pass is this total time, so that's at 40.2 days divided by my half-life is 0.84, gives me that we've had 5 half-life expire. We've had 5 half-lives take place, so that gives us our n value. So the n goes there, and we want to solve for r. Note that this doesn't have r in the formula, but we said before that n is proportional to r, so I can just replace in this formula our r values. And again, I'm going to just put the r in this 2 in the denominator, and then solve for r instead of r naught. So I rearrange the formula. So we have this 6.4 millicuries, 6.4 millicuries, and I'm not going to convert to decays per second because we want our answer in millicuries. So 2 to the 5th is equal to 0.2 millicuries should be what my new rate is after this amount of time.